Okay, our next speaker is Naomi Halas. Naomi is another great example of a card-carrying physicist whose impact and intellectual contributions include not only physics, but extend beyond to other areas of science. Naomi is the Stanley Moore Professor in Electrical and Computer Engineering, Professor of Biomedical Engineering, Professor of Chemistry, and Professor of Physics and Astronomy at Rice University. She's also the founding director of the Laboratory for Nanophotonics. Naomi is one of the pioneering researchers in the field of plasmonics. She created the concept of the tunable plasmon and invented a family of nanoparticles with resonances spanning the visible and infrared regions of the spectrum. She pursues fundamental studies as well as applications of plasmonics in biomedicine, optoelectronics, chemical sensing, photocatalysis, and in solar energy. She's the author of more than 250 refereed publications. She has more than 15 issued patents, has presented more than 450 invited talks. You must be exhausted. And her work's been cited more than 30,000 times. She's the co-founder of Nanospectra Biosciences, a Houston-based company developing photothermal therapies for cancer and other diseases based on her nanoparticles, which are currently in multiple clinical trials. And she's the co-founder also of Eureka Sun. Naomi is a member of the National Academy of Engineering and the National Academy of Sciences. She's a member of the American Academy of Arts and Sciences, a recipient of the 2014 APS Frank Isaacson Prize for Optical Effects in Solids. She's a fellow of many professional societies, including the AAAS and, of course, the American Physical Society. So please join me in welcoming Naomi Halas.
Very good. Thank you. Thank you so much. And I want to thank, first of all, the Kavli Foundation. I am so lucky because I was actually in San Diego on Monday and I got to hear the Kavli Symposium on the Frontiers of Chemistry, which was really fabulous. So I'm so happy to actually hear these. I'm so happy that you included me in this list of really wonderful speakers. So I'm going to talk about metal nanoparticles. I understand there was just a brief question though at the end of the last speaker's talk about gold colloid. That's kind of our starting point, but we're going to go quite far afield from there, and I just will give you a very brief outline of my talk. I'm going to explain to you why plasmonic nanoparticles, why these really are artificial molecules in a rigorous way, and I'm going to leave the world of noble metals, gold and silver, and move into aluminum, because I think sustainability is very important, and I'll talk about that a little bit. And then I'm going to talk about how plasmons can be used to obtain hot electrons and how we can begin to do some very interesting new things with hot electrons that range from both physics and chemistry, and also talk about another phenomenon that is related to nanoparticles in light that we have been looking at in the most recent couple of years that we call solar steam generation, where we can generate steam without boiling water. So this is a picture from high school chemistry books these days. This is a cup found in the British Museum, which is probably familiar to many of you. It's about 2,000 years old, and the material is glass where gold nanoparticles are embedded. And the first homework problem of classical electromagnetic theory was an incident plane wave on a gold nanoparticle in the electrostatic limit. And back about 100 years ago, Gustav Mies solved that problem for a solution of Maxwell's equations using the best dielectric function data that they had at the time. And he showed that why gold actually, when it's a very small nanoparticle, absorbs green light and therefore transmits red light. And that's the origin of this beautiful color known as ruby glass, also found in stained glass windows across Europe. So if we manipulate the geometry in simple ways, we can manipulate the color of gold nanoparticles. And this is sort of the next simplest way to do things. Rather than having a solid sphere, have a hollow sphere. And this was, of course, also very old as an analytical solution, was solved back many years ago. And this was a starting point for our own research in this field to be able to make structures like this and control the inner and outer radius of the shell, which is the way that you tune the plasmon on a structure like this. So what is a plasmon? A plasmon is an incompressible electron cloud in a piece of metal. So when we learn about metals, we learn about infinite metals or perhaps one interface, a surface. But when we have a finite metal, then the collective electron cloud actually will have coherent oscillations, and those coherent oscillations of the incompressible irrotational electron gas are known as the surface plasmons, and also when the structure is much smaller than a wavelength of light, it can be optically excited. So a macroscopic metal is, of course, a mirror. When a metal is smaller than a wavelength of light, you can directly excite the plasmon oscillations in the metal. So if you're a chemist, you can go and do exactly what I showed you. You can make these little gold particles that were like the ones that were in the beautiful goblet. And you'll have one resonance, as we see here. If I take my gold structure and I stretch it, and chemists know how to do that, I'd make, instead of a sphere, a rod. And so the electrons, now we have broken symmetry, the electrons can oscillate either along the longitudinal direction, so they have a lower energy resonance, or on the transverse direction, and they maintain the same resonance as a sphere. If I don't want anything to do with chemistry, but I do know how to do E-beam lithography, I could make similar structures like a block and a rod. And although I'm using different tools, the physics is essentially the same. And this is why this field is just as popular within the chemistry community as it is within materials science and physics as well. The tools are a wide range of tools allow us to access the same physics. And so what happens when we bring particles together? So what's very interesting about metal particles, so say I have a metal particle and it's got about 10,000 atoms, therefore I have roughly 10,000 electrons in its, that will form the plasmon, this incompressible electron gas. Well, when I bring this next to another one, then these two electron clouds, multi-electron electron clouds will mix and hybridize according to the laws of quantum mechanics. And so just as we can take two atoms, like two hydrogen atoms, bring them together and form molecules and form a different spectrum of molecular orbitals, the same thing happens when I bring two nanoparticles together. Then the energies change, and I form bonding and anti-bonding orbitals when these begin when they begin to couple to each other. And so this is a rigorous way to calculate and also an intuitive way to understand what happens when we begin to bring particles together and make what are essentially artificial molecules. So want to give you a very simple example of this. If I take two gold nanoparticles and I bring them together, what I see is quite a dramatic color change. So the first thing is I show you a liquid solution of isolated gold nanoparticles, and it absorbs green light, just as I showed you a moment ago. It appears red to the eye. If these begin to come together, then I see quite a dramatic color change. This is now they absorb red light, and so they transmit the complementary color, so I see this bluish. And this red-blue color change actually was the first application of plasmonics in real technology. So this is the world's first plasmonic device. About half of you may have, many of you know what this is. Many of you have used this. This is a microfluidic device. We're going to use our nanoparticles to measure the presence of these molecules that are appearing as little green dots here. And so I can address gold nanoparticles with antibodies. That's what those little structures are meant to be. And as as they capture the molecules, they move down this microfluidic channel to the second region where there are also gold nanoparticles. They bind together and form dimers. And as I just showed you a moment ago, this corresponds to a color change. And so if that's not, haven't guessed yet what that is, that's actually a home pregnancy test that you can buy in any drugstore. And this is the fact that the cross-section goes with a number of electrons. So unlike dye molecules, you will have an optical cross-section that might be 10,000 times larger than you would with dye molecules. Then you have increased sensitivity, and therefore you have earlier detection times when you use plasmons. So this idea of plasmon hybridization spawned a whole variety of different types of shapes and sizes that we can, of nanoparticles whose plasmon resonances now we can rigorously understand, we can design before we make them, and have a lot of different types of properties, and just show you a large variety of shapes and geometries here. And some of them do look a lot like artificial molecules. And just like molecules, you will find that there are dipole allowed and dipole forbidden states, or bright and dark states that couple to light and some that don't couple to light. And those give rise to coherent effects. So effects like phonoresonances and superradiant, subradiant modes that we expect more from atomic and molecular physics. We can also design into metallic nanoparticles through hybridized plasmon modes. So gold and silver have kind of been the canonical origin of this field, but I decided to take a lesson from history In particular, I took this lesson from history when I began to hear about people using plasmons to enhance solar cells, and I thought, well, are we going to really put gold nanoparticles all over our roofs when we have enhanced solar cells? And so I learned an interesting history lesson from what's a really great book. If you have time to read, if you want to read a book about science, then this book called The Idea Factory is a fabulous book. And of course, we all recognize what's in the top right corner, and that is the first transistor that was made, and it was made with germanium. Germanium is not the least expensive material. Germanium was relatively scarce. Even then, they realized that germanium was quite scarce. And so, following as the dust settled after the first, after the invention of the transistor and all the incredible media attention that was made and all the vision that people had about how the world of electronics would change from vacuum tubes out to the solid state, people then also began to realize that eventually electronics would be limited if they did it in germanium. And so people knew nothing about the properties of silicon. They made the extra effort in the early 50s to begin to learn about and to control the properties of silicon. And if you think, so this was, if the transistor industry, which is what they called it then, was potentially as enormous as everyone was envisioning, then germanium scarcity and its high price at some point would limit industry's growth. And so, so we can just think about our smartphones that we have. If they were actually made out of much more costly materials instead of the very inexpensive silicon, then the world would be the world as we know it would be a very different place. So when we think about metal nanoparticles and gold and silver, we can also ask the same question. Perhaps we should be looking at materials that are much more abundant if we want to think about making something like a smart window or a roof covered with solar cells enhanced by the plasmons. And so if we look at a chart of the abundance of metals, metals at the Earth's surface, we see that gold and silver are down in the more rare metals, but aluminum is in fact the most abundant metal at the Earth's surface. And so we can begin to look at the properties of aluminum. Aluminum has a plasmon resonance that one can tune across the visible and the ultraviolet region of the spectrum, not unlike silver. But unlike silver, it's actually remarkably stable. Silver oxidizes very readily. So does aluminum, of course. It's highly reactive. But it forms an oxide that then arrests further oxidation. So it has a very stable oxide layer. We all know this because when we buy aluminum foil and we put it in our kitchen drawer, we don't expect it to spontaneously combust. And, of course, it doesn't. So aluminum is also quite manufacturable with CMOS compatibility, and the price scales, of course, with the fact that it is and always has been an abundant material, and the cost is related to the cost of the cost of refining. So one can make structures, just as I showed you before. You can make aluminum nanostructures and see beautifully well-defined plasmons, longitudinal and transverse plasmon modes. That, of course, agree beautifully with theory. And then we can almost immediately go from this idea of making aluminum nanorods and show how they span the spectrum to an application. And that application has to do with making a display technology. So these flat panel displays that we are used to using are often made of a variety of different types of materials, materials that have lifetime and processing issues, and aluminum is actually much more trivial to process. So what I'm showing you here are a variety of different pixels, a range of different pixels that are very vivid that are all made out of aluminum. And so one has aluminum nanorods, as you can see here. And so the secret to the vivid color that I just showed you is the fact that you have nanorods and you can tune the color by the aspect ratio, but you also can make them vivid by formulating the nanoparticles, the nanorods, all oriented in periodic arrays. And so you use both the periodicity of the array and the optical effects that you can obtain, plus the nanorod resonances to give you very sharp, vivid colors. And so the optical name for this is called far-field diffractive coupling, which gives rise to a very strong narrowing of the optical spectrum. And you can see here, if you just look at the color, right? The spectrum, of course, gives us a color. If we look at the color of an individual nanorod, we see these very faint, pale colors, which correspond to a very broad spectrum. If we used far-field diffraction and we use the array in intelligent ways, we can narrow the spectrum very dramatically and give rise to much more intense colors that actually will give us something that's red, green, blue accessible that's completely competitive with what one can actually go to an electronics store and buy. So it's quite easy to do. So another thing that plasmons do, so we think of these as sort of small optical objects that act like antennas. But another thing that they will do when we excite a plasmon, so that's my little cartoon of an optical excitation of a gold nanoparticle and the conduction conduction electrons. So once we excite once we excite a plasmon, the plasmon can decay several different ways. It can decay radiatively by scattering a photon. It can also decay by the excitation of an electron-hole pair. And so the electron-hole pair corresponds in energy to the resonance, to the energy with which I've coupled light into the nanoparticle. And if I excite, say, for example, a cold hole and hot electron, so whether the electrons and holes are hot and cold depends on the electronic structure of the metal, but in a simple metal like aluminum, if I excite the electron-hole pair, the electron will be hot. It will actually extend out from the surface, and so it's available now to do to perform other tasks. So this is something that the chemists knew quite some time ago, and looked at how one can basically excite the electron fluid, and then for hot electrons, how hot electrons could transfer into the unoccupied state of a molecule and do chemistry. But we don't have to do this with molecules. We can do this with any kind of electron acceptor, so we can do this with a very simple solid. So let's look at an experiment that we can all understand very easily. We can make a Schottky barrier where the metal of the Schottky barrier is a little nanorod. And so this is the nanorods here in the center. And so if we excite, we can optically excite the nanorod. We excite a hot electron. If the hot electron has enough energy to make it over the Schottky barrier, it will transfer into the semiconductor, and we can then collect this as photocurrent. So I'm no longer limited for generating photocurrent by the band gap of the semiconductor. We always think that's, of course, the limitation in terms of how low a photon energy I can detect with a given detector. Now the limitation is not the band gap. The limitation is the Schottky barrier. And so we call this a nano antenna diode, where the metal is basically the nanorod, and so as we can see, the nanorod length controls the spectral selectivity of the detector now. So if we change the length of the nanorod, we detect light at different wavelengths, all below the band gap of silicon. And of course, this is a polarization sensitive nanorod, so the detector now is polarization sensitive. So in a certain way, the nano antenna has taken over the light detecting properties of the silicon itself. And this is a little cartoon for what this looks like. So here we have a nano antenna. We excite the plasmon optically, and then we inject hot electrons over the Schottky barrier, and the nano antennas are electrically connected so that we can complete the circuit, and we have a photocurrent resulting. So another thing that we can do with hot electrons, as I mentioned a moment ago, is we can transfer them into the unoccupied orbitals of molecules, and we can actually use this to do chemistry. And so I realize I'm speaking to a group of physicists and not chemists, so I'm going to talk about the simplest chemical reaction that you can probably even measure. So even if you're chemistry averse, my goal is for you to understand this. So we call this the impossible reaction. And what this is basically a dissociation of hydrogen. So H2, the H2 molecule is like helium. Right? It won't even stick on surfaces. It is a very, very inert. The dissociation energy is extremely large. But if I were to put an extra electron on that molecule, then the dissociation energy drops pretty dramatically, and it's relatively easy to dissociate. So what we do is we flow our hydrogen molecules over a surface of colloidal nanoparticles. They might weakly associate with the surface, but then we excite the plasmon in the metal. The plasmon decays to generate a hot electron, and that hot electron transfers to the LUMO level of the molecule, okay? And then the molecule dissociates. It falls down to this repulsive potential, and we see a dissociation of the molecule. And so we can basically do light-induced dissociation, right, all at room temperature very easily. How do we measure this? We measure this by flowing H2 and D2 And so if we're going to actually dissociate the molecules, we should form HD. So I just look at the mass of the molecules when we turn light, when we illuminate, and when we do not illuminate, and we see that when the light is on our system, that we're able to generate HD quite well. It's not a thermal effect at all. It is a purely light-driven effect, so it is a direct charge transfer. And we can see it actually has a wavelength dependence that's directly related to that resonance of the gold nanoparticle that I showed you earlier. So I mentioned aluminum. Well, we like to, as I said before, gold nanoparticles are quite interesting and have this plasmon resonance, but so do aluminum, and aluminum is in principle much, much less expensive. And so we've developed a way to make, just in analogy with colloidal gold, to make colloidal aluminum nanocrystals. They're not, they're beautiful faceted structures. We can control the diameter of these structures, and we can look at their, at the scattering spectrum of the individual nanoparticles, so we can see the size-dependent resonance, but we also see something quite interesting. On the left-hand side of this scan here, so those are the 4 particles that we're looking at. This is the dark field scattering spectrum of each individual particle that I'm showing you. On the left-hand side is the experiment, and on the right-hand side is the theory. And immediately we see something very strange here. How can my theoretical peaks be broader than my experimental peaks? Well, it's because we're using the dielectric data, the dielectric function data obtained for bulk aluminum. But when a nanocrystal grows, it's one of the purest forms of matter that we can obtain, because as it grows, it forces the impurities to the outside in a quite perfect crystal forms. And so the optical properties are such that they're indicating to us that the aluminum is extraordinarily pure. And if we look at the elemental map of an individual nanocrystal, we see that alumina layer that I mentioned before. It has this between 2 and 4 nanometer capping layer that is robust with respect to further oxidation. And so we do the same experiment. Can we also take H2 and D2 and shine light using aluminum nanocrystals and obtain a similar type of result? And yes, they are just as catalytic as the noble metal, but with a slight change, and that is that the electronic structure is quite different from aluminum. In aluminum, you have a D band above the Fermi energy, and that actually results in a large in a high density of hot electrons at an interband transition that's at lower energies. And it turns out that the interband transition, more than the plasmon energy, so that you can see the spectrum here, but the interband transition gives rise to the most production of hydrogen dissociation. So I want to switch gears a little bit and talk about another phenomenon that we've been very interested in the last couple of years, and this involves how to make steam. So everybody knows how you make steam, right? You boil water, you take a vessel of water and you heat it up, and you wait, right? You wait a long time because you have to raise the temperature of the water to the boiling point, and that consumes a lot of energy. And then once you wait and your water reaches 100 degrees Celsius, then you will produce some kind of steam. Or you could do something else. You can take your vessel of water and you can put light-absorbing nanoparticles in the water, and then you can shine light, and you will, in fact, immediately see steam produced. And not only will it be produced immediately, but it will be produced at remarkably high efficiencies. So let me show. You can even put it in an ice bath. You can put it in an ice bath. So we have this interesting effect where we seem to be separating steam production from steam generation from boiling water. So I'm going to show you a quick video. So I'm going to have to describe what this video looks like first, because the video goes very quickly. So we take a solution of light-absorbing nanoparticles, and we stick a thermocouple in the bottom of our little test tube, and we put the whole thing in an ice bath, and then we shine light. We focus sunlight onto the test tube, and after a few seconds, you'll see actually quite explosive boiling or steam generation. Okay, so here we have our thermocouple at the bottom. That's a timer for dramatic effect. And there's our test tube in ice, and we focus sunlight. So you can see we don't use a solar simulator. We actually use sunlight, and you can see that within less than 12 seconds, we had a release of steam, and the steam was the temperature of the water remained at 0 Celsius. So we can look at the energy distribution. We can do the experiment again, and again we're working outside. This is our solar simulator is really the sun. So we take a solution of nanoparticles, and we focus sunlight on the solution. We have a thermocouple, but then we also put the whole thing on an analytical balance. So that way, when we measure the mass loss is the steam generation. So we can measure both the increase of the fluid and the steam generation rate simultaneously. And we can use a variety of different nanoparticles. The only constraint on the nanoparticles is that they both absorb and scatter light, and I'll say something more about that in a moment. So we use gold because it's convenient. We make gold nanoshells very readily in our laboratory, but we also use inexpensive carbon black. And so if we take a volume of water, mass of water, right, and then if we follow the temperature increase, we know exactly, this is basically the heat capacity, the mass, and then delta T. So if we have a larger mass, we have a smaller temperature increase, a smaller mass, larger temperature increase. That's all exactly what any junior high school or high school physics student would expect. If we look at the mass, if we look at the mass loss at the steam generation rate, it's identical. And if we just measure, say, in this 4-minute window between 4 and 8 minutes, then what we find is that the amount of energy used to heat the fluid and the amount of energy used to generate steam are quite different. And so about 80% of the total incident energy goes directly into steam production and not into fluid heating. So what could be going on here? So if we solve the heat transfer analysis, so some of you might be feeling very uncomfortable at the moment as I describe this. And you wouldn't be the only one. So if you just go and you solve the standard heat transfer analysis, of course, what you're thinking is these are particles embedded in water. It's a water bath. The water has got to win, right? And if you just go through the numbers, you find that there should be no temperature increase at all, right? A minute temperature increase, like less than 1/10 of a degree. So what in the world is going on? Are we actually generating steam? And the answer is definitely yes. And we weren't the only ones who found this was very strange. We were doing individual particle experiments, and we found that the energy needed there for making a bubble around an individual particle was very different than what we were observing. And we weren't the only ones. So this beautiful review article was written right after our paper came out, where they looked at people who were doing laser experiments with bubbles and nanoparticles, and they all had data over here. And our data was over here, and they wrote this nice paragraph about us. The puzzle is that the theoretical estimate of the nanoparticle temperature rise in 25, that's our paper, which is based on the calculation of the absorbed power in the solution of the Fourier law heat conduction equation, is only 0.04 degrees Celsius. So we agreed there. So what could be going on? So it turns out that what's going on is a very interesting, basically a lesson in optical trapping, or for some people, you can think of this as a variant on the weak localization of light, where if we have a solution of nanoparticles. So in the world of weak localization, so some of you might be people who study this, you know that you look at the scattering properties of particles, the light scattering properties of particles, but you always make sure that those particles are lossless. Well, here we have to have loss. We have to have absorption because that's what drives this particular effect. So we're looking at this type of light localization in a regime where physicists typically don't want to study at all, and that is where the particles both are absorbers and scatterers of light. But if we think about each individual photon entering the flask, so this is just a cuvette irradiated from above, and we have nanoparticles that both absorb and scatter light. So what happens is each incident photon will scatter once or twice or some multiple times until it gets absorbed. And so this multiple scattering, which is, of course, a function of the concentration, this multiple scattering will actually confine the light energy into the thin region near the water-air interface, and where the absorption then occurs as well. So the light energy gets absorbed in this very thin layer near the surface. And so to test this, what we did was we did a laser experiment, and we designed 2 different nanoparticles that had identical absorption, but depending on the properties of the particle, one particle scattered much more than the other. So it was like we were tuning the scattering cross-section and keeping the absorption cross-section identical for the nanoparticles. And so these are the nanoparticles that we used, and these are the absorption and scattering cross-sections that I'm showing you right here. Nanoshells are one, and then we heard some reference to nested Russian dolls in the last talk. So that Russian word is nanomatrushkas, and so these are plasmonic nanomatrushkas, which are absorbers and not scatterers. So then if we look at the same experiment that I showed you before, a cuvette of fluid filled with nanoparticles, illuminated from above, what happens to the light energy as it gets absorbed? And we change the concentration of the particles. And for the case where we have particles that scatter, so here we're increasing the concentration by 1 order of magnitude as we go from left to right for the scattering particles, and an order of magnitude again, 1 to a factor of 10, factor of 100 for the particles that are absorbers. And what we find is that for high concentrations for the scattering particles, we have a much smaller volume, a tiny compressed volume of just a few microns where all the light energy gets absorbed relative to just when the particles absorb light. So the light is really a light trapping effect, which keeps all the light energy in a narrow volume near the surface. And those were simulations, and so we wanted to see how good are our simulations. So our simulations then, rather than simulating where the light's absorbed, we said let's simulate where the light comes out, okay? And that means we should be able to go into the laboratory and take photographs of the cuvettes. And so these are photographs of basically the 3 different concentrations, and it shows you how different the light energy is. And for the highest concentration, we even see backscattering of light out of the vessel. And that, when this correspond to our simulations extremely well. And so that gave us a lot of confidence that we were seeing, and we were in fact going to be able to emulate the ice bath experiment that I showed you, where we have steam forming at the top, all the energy concentrated at the top, and literally 0 temperature increase at the bottom of the vessel. And that's exactly what we're seeing here for either particles that scatter light or particles that absorb light. So it's fun to make steam, and it's interesting to make steam and see it by this other method, but we thought it would be even more fun to make whiskey. And so there aren't enough graduate students here, so they didn't catch this. So why don't we look at liquid mixtures and to make steam from a liquid mixture and then condense the liquid mixture is a process called distillation. And what you might not know, distillation is one of the most energy-consuming processes done by the civilized world. It consumes a huge amount of energy. It's often not considered when we look at total energy consumption because it is because chemical industry that does this has their own energy grid. And so it has different, so for example, for biofuels, 70 to 85% of the cost is in that one process of distillation. So if we can make distillation, if we can make distillation more energy efficient, then that's a pretty tremendous goal. So we go back outside to our solar simulator with water and ethanol, and we find that first of all, we make a lot of ethanol right away, as opposed to the thermal process where we have to heat up our water ethanol mixture. But then when we actually look at the distillate, we find that it's much richer in ethanol than what we would normally find from our standard water ethanol azeotrope. And those of you who remember your chemistry books or your physical chemistry book, you saw this water ethanol distillation curve. And then at about 9.95 mole fraction, you can't distill any further, and you have what's called an azeotrope. So we saw this very unusual distillation curve, but it was also very noisy because we did this experiment outside. We have to go inside, do it in a clean environment, and what we find, in fact, that we have an extraordinarily clean way of distillation, and we actually have 0 azeotrope in the case of a water ethanol distillation. So we thought this was wonderful. This is a revolution. We'll completely change the way in which liquids get distilled. So we have this remarkable result with ethanol. We added 1 carbon to the chain to the alcohol, and instead of having ethanol, we had propanol, and a propanol water mixture, it turns out, was identical to the thermal result. Now, why is this? We understand this because water ethanol forms a very strongly hydrogen bonded network. Propanol and water form a much weaker hydrogen bonded network. And what we're doing is we're distilling with these little nanoscale heaters. And so we believe that the mechanism is very strongly tied to the fact that they can disrupt the local hydrogen bonding network. And that's the mechanism for the enhanced ethanol vaporization that we see in this experiment. So So to conclude, I've talked to you about some of the basic properties of plasmonic nanoparticles and how we're excited about new sustainable materials like aluminum, and how we can also do some interesting hot electron photophysics and photochemistry like photocatalysis with aluminum nanoparticles instead of these very expensive types of nanoparticles, how we can also harvest light in interesting ways and generate steam in a new way, and how we can also use that then to separate liquids that have a tremendous commercial impact. So with that, I want to again, I want to thank the funding agencies, and I want to thank the many people in my group and many collaborators, and the wonderful criminals that I get to work with day after day. So I'm more than happy to answer questions.
Thank you, Naomi. That was brilliant. I just want to know if you and Peter have a nanoparticle still on your ranch.
No, but we have a name for it, so we would call it Sunshine.
Sunshine. Oh, my God. That's awesome. We have time for a quick question or two for Naomi, right in the middle.
What are some of the developments or challenges that would be necessary to scale up plasmonic particle production to make large-scale applications like displays, photovoltaics, steam generation, going beyond just the laboratory scale?
That's a gregreat question. I think that certainly for manufacturability, this is actually much aluminum, say for flat panel type. It's compatible with electronics, right? So all of that type of manufacturing technology is in play for aluminum. So, as you might be aware, in electronic devices made out of silicon, you can't use gold and silver at all. But here you can use aluminum, and you can also use copper as well. Copper has different properties, but it's also very compatible. So, but aluminum is really ideal in that sense for some of the for the process that I just described with steam generation. So clearly, one wants to make some kind of a transition from batch processing to a flow type system, and that's an interesting system. It's certainly not without its challenges, and there are a lot of people who are looking at ways in which we can do scale up with that.
Question over there.
Yeah, for the surface plasmon resonance, omega equals N0e divided by the dielectric constant times the mass square root. Does that approximation take into account the zeta function solution to the wave equation, which is not Euler's solution, but a rather distinct polynomial solution, where we have the recursion relation that defines the wave? These are classical waves from electrodynamic theory and not novel Riemann surfaces.
Yeah. So for much of what for optical properties, much of what one can do, there are ways in which quantum effects really begin to emerge as major in major regions of parameter space, but certainly for spheres, that's not one of them. So classical electromagnetic theory can describe this very well. So that, of course, the formula that you mentioned was appropriate for spheres, and we're, of course, looking at for every time you modify the geometry, then there are obviously modifications to that. So what people typically do is they are, this is a wonderful application of computational electromagnetism. So you can solve any kind of arbitrary structure, even with all of its defects and so on. You can obtain the optical properties, very, very good correspondence between optical properties of nanoparticles and nanostructures, between the theory and the experiment. So thank you.
Okay, please join me in thanking Naomi again for a beautiful talk.